Okay, let's now turn our attention to the chi-squared distribution. This is in 11.1. So the chi-squared distribution changes shape as a function of sample size, similar to the student's t-distribution. The student's t-distribution remains symmetrical when the sample size changes. So what we've got here down below is actually the student's t, and you can see here sample size is going up. And as sample size goes up, the peak here at the center of the distribution also tends to go up. And as sample size goes up also, the tail of the distribution gets a little thinner. Okay, so the student's t-distribution tends to shapeshift a little bit. And the higher that the sample size gets, the closer it approximates a normal distribution. The thing to remember about the student's t-distribution is that it is symmetrical and it has negative and positive values of x. So, here we've got 0 in the middle. We have positive values to the right and negative values to the left. And it's symmetrical about this line of symmetry right down the middle. By contrast, the chi-squared distribution changes from non-symmetrical at low sample sizes to approaching symmetrical with higher sample sizes. So this is actually a chi-squared distribution here that you see in these three graphs. So you can see it changes shape quite a bit compared to the student's t. So at low sample size, it's got a curve that looks like that. When the sample size goes up, it actually now has a bit of a peak. It almost looks like a right skewed distribution. Okay, and at higher sample sizes, you can see it has this approaching being symmetrical. Okay, but it still does look slightly skewed to the right. But the thing to highlight here is that the chi-squared distribution only has positive values. Only has positive values. You can see here's 0, and it only has positive values. All right. So, of course, in contrast to the student's t, which had positive and negative. And the consequences of this is that when we do hypothesis testing, the hypothesis testing is only going to be right-tailed. Okay. It won't be left-tailed and it won't be two-tailed, right? Because it's not symmetrical. Okay, so that's going to make, I think, doing hypothesis tests a little simpler when we do hypothesis tests around the chi-squared distribution. All right, so the critical values and the test statistics we calculate are only going to be positive numbers. Now, with the chi-squared distribution, okay, we have degrees of freedom, which is the same as what we found with the student's t-distribution. So degrees of freedom is equal to the sample size minus 1. Now, the population mean of a chi-squared distribution is simply equal to the degrees of freedom. The population standard deviation of a chi-squared distribution is equal to the square root of 2 times the degrees of freedom. So just remember that a chi-squared distribution curve is non-symmetrical and skewed to the right. That it's shape-shifting, so there's a different chi-squared curve for each degree of freedom. And where the degrees of freedom is greater than 90, the chi-squared curve approximates a normal distribution. But again, I think that's a little misleading because it's not symmetrical with positive and negative values. That's just kind of like the overall shape. And then the other thing is that the mean of the distribution is located just to the right of the peak. So what do we mean by that? So we can see here, here's the peak. And so the mean, if that was our distribution, would be just to the right of it. So somewhere right about there, just to the right of it, somewhere right about there. Okay. So that's what we mean by that. Okay. So, I mean, that's just our short and sweet introduction to the chi-squared distribution. We'll be doing something with it here next. Let me know if you have any questions.